Welcome to Study Loop.
Okay, we have a picture of an amino acid, aspartate specifically, as it changes in different environments. Specifically, we see the subsequent deprotonation of the various functional groups, being in this case carboxylic acids and ammonium in our aspartate. And that at each step of the way, we will lose another proton, and with it, change the overall charge of the molecule. Sorry, I'm trying to talk while I draw this to not waste your time. Until we reach such a point that we have lost all labile hydrogens and have only have a net charge of -2. So we go from a net charge of +1, and then as we increase the pH, we lose this proton, and at that point we have a net charge of 0 until we increase the pH, right? And we lose this proton until we once again increase the pH until we finally lose this proton, or one of these protons. In fact, let me draw this a little differently to make it, I'm going to say H2 and then explicitly just show a proton sticking off so we can show that it's one of the protons on ammonium. Okay, until finally we have a charge of -2. And so I guess your question is understanding how the net charges are obtained at different pKa's. And I would say that it's not at different pKa's. pKa is involved, right? There's pKa1, pKa2, and pKa3. And what this is relating to is that the lowest pKa, meaning the most labile proton or the easiest, most acidic proton in this molecule, oops, I forgot a couple charges, is this proton. That's the one that's easiest to remove, right? And so the pKa associated with that proton is pKa1. And so what we're really doing as we move across from left to right is we are increasing pH of solution, which contains aspartate, right? So the idea is if you put aspartate in a beaker at, say, neutral pH, or let's say acidic pH, you would find that both carboxyls as well as your ammonium would be fully protonated. Now, as you add some sodium hydroxide, let's say we add NaOH, increase the pH, the proton on this carboxyl would come off, right? And if we add a little more sodium hydroxide and increase the pH even more, eventually this proton will come off, right? And finally, if we increase the pH even more by adding even more sodium hydroxide, this is just an example, by the way, the sodium hydroxide, further increasing the pH, eventually we'll be able to strip the proton off of our ammonium. Okay, so that's all that's going on here. This is a chart showing us that as we increase the pH of our solution, the charge of our molecule will change, because the more basic our solution is, the less protons will be retained by our molecule. Protons are, if you recall, are H plus, which is why each time that we lose one, our charge goes down. We lose another one, our charge goes down. We lose another one, our charge goes down. This is really just showing the progression of the various protons that are able to be abstracted off of aspartate, and in what order they are removed as we increase the pH of the solution which contains aspartate, and additionally what the overall charge of our molecule is at every step of the way as we increase the pH to subsequently remove more and more protons. Hopefully that helps.